Video we're going to discuss polar graphing. The major thing to understand about polar graphing is that it takes any point that you represent on a rectangular or Cartesian plane x comma y, and it just re-represents it in a different way. So this point x comma y has a rectangular representation because we go over by x units and then we take a 90-degree turn and we go up by y units. So you can think of it as walking on a city blocks where every street is laid in a grid. So you have to walk over x blocks and up y blocks. Well, the polar graph does something different. It starts you at the origin and then it says orient yourself directly facing the end point x, y. And it says then figure out what the angle is to go from here to this point, and we call this angle theta. So that's the angle of elevation between the x-axis and the line directly pointing to the point xy. And then it says go, so after you've pointed yourself in that proper direction, now you walk out exactly r units. So it's the shortest distance between the origin and the point. So if we go back to the city blocks examples, so you're on city blocks, well imagine now instead of walking the city blocks, you could sort of take a helicopter or something, fly directly to that point. The first thing you'd want to do is orient to that point, and then the next you fly directly to it. So we can come up with three equations to relate x's, y's, and r's. The first one is very simple. It's just that x squared plus y squared has to equal r squared, and that's just a simple Pythagorean theorem. We've got x, y, and r here, and it's a right triangle by virtue of the rectangular coordinate system. For the next two equations, we'll have to observe that cos theta is equal to the adjacent over the hypotenuse, or x over r, and that sine theta is equal to the opposite over the hypotenuse, or y over r. So x is r cosine theta, and y is r sine theta. So this gives us three equations, and these three equations are going to allow us to go back and forth between rectangular and polar. So you might ask if I can represent a rectangular point as polar, well, why bother? And there's a good reason for this, and the reason is that sometimes certain objects that you are graphing are better or more easily or more concisely represented in polar form. One such example is the equation x squared plus y squared equals 1, which hopefully you recognize as the unit circle. So this is a circle with radius of 1, and it's got the center of 0, 0. But in polar form, if you just take x squared plus y squared and you replace it with r squared, you get 1. But a simpler statement of that is if the square of a radius is always 1, well then the radius itself is always 1. So we're ignoring a -1 radius. We'll talk more about that in a bit, what it means to have a negative radius. So r equals 1 is a very concise way of stating x squared plus y squared equals 1. For example, if I was to say to you, draw an object whose distance from the origin is always 1, you'd have no problem doing that. You'd know that it just makes an orbit about the origin. But if I told you, tell me the set of all points whose coordinates squared and summed are 1, it's probably a little difficult for you to just immediately conceive of a circle. So let me give you a different example where you probably have no background knowledge, and that'll be 1 plus sine of theta. So I'm going to graph 1 plus sine of theta here. In order to graph these, we need something called polar paper, or some sort of means of graphing the polar in a little bit easier fashion. And see in the rectangular, that's why we use graph paper in a rectangular, because it has a little grid built on it. Well, polar paper kind of looks like this. So wherever your radius of 1 would be, there's just a little circle there, and then radius of 2. So this is the set of all points whose distance from the origin is 2. And then a radius of 3. I realize that it's not perfect, but it's good enough. You'll see how we'll use that in a second. So all we're going to do is pick varying values of theta, and then graph. So if theta is 0, then we'll have 1 plus sine of 0, which is 1. And I encourage you, as I name values of theta, press pause on the video and see if you can calculate it for yourself and graph it. So this means we point ourselves to 0 degrees and we output an r of 1. So this is the point where the radius is 1 and theta is 0. By the way, the ordered pairs are listed sort of a bit oddly in r comma theta form. So we kind of treat this as the input for our equation, but the r comes first by convention. So this is the point 1, 0. Now let's plug in a theta value of pi over 2. Well, calculate that, you'll get 1 plus 1, which is 2. So that means, first of all, point toward pi over 2, or 90 degrees, and then go up 2 units. And we still haven't really needed our little circle polar paper here because everything's been on the axes. But if you want to know what happens in quadrant 1, pick a value like pi over 4. So that'll be 1 plus sine of pi over 4. Sine of pi over 4 is root 2 over 2, which is approximately 0.7 or 0.707-ish. Let's call it 0.7. So we'll have 1 plus 0.7, which is 1.7. So that means we need to, first of all, examine the line of pi over 4, and then we go out 1 whole unit to the first orbit, and then we don't go quite all the way to the second orbit. So we'll go, I don't know, this is attempting to be 1.7 units from the origin, and then we get an image like this. And now, since it's the sine function, remember sine's outputs are the same for quadrant 1 and 2. So if I were to do 3 pi over 4, I'm going to get the same exact output of 1.7. But somewhere around here, if I plug pi in, I'll leave it to you to calculate. But it's 1 plus sine of pi is 1. And we close back up. If you're wondering, like, how did I know to draw this particular arc, I encourage you to plug in pi over 6 and pi over 3, and you'll get a little bit more data for yourself, and you'll be able to trace the path of that arc a bit better. Now, at 5 pi over 4, that's 1 plus sine of 5 pi over 4. That's 1 minus 0.7, roughly. So that'll be about 0.3. So I'm in the direction of 225 degrees, but I'm only going to go 30% of the way to this first orbit. And then at 3 pi over 2, or south on the graph here, that'll be 1 plus negative 1, which is exactly 0. So that means the object closed back in on itself. And then if you plug in 7 pi over 4, you'll see the same output of 0.3-ish. And you can draw the rest of the shape. So this thing has a name. It's called a cardioid. Just think cardio or heart. It's heart-shaped. Okay, so one thing I'm going to do is color code here. I should have done that before I graphed. So now the black equation matches the black. Now we'll graph 1 plus 2 sine theta. I'm going to graph that in red. And you'll see there's some notable differences about this graph. One thing that I hope you saw about the black graph was that it was maximal in terms of its radius at a value of pi over 2, because sine is biggest at pi over 2, and thus the radius is biggest at pi over 2, and that's what pushed it furthest from the unit circle here. Same thing happens with the red guy. It'll be 1 plus 2 sine of pi over 2, and that's 1 plus 2, which is 3. So it just makes it a bit further from the origin for that particular value. Let's go back to 0 degrees though. 1 plus 2 sine of 0, that's actually the same exact point, so it's going to be hard for you to see right now, but there's a red point here as well. Now let's go to pi over 4. This would be 1 plus 2 times sine of pi over 4. Now that's 1 plus 2 times 0.7, or 1 plus 1.4, 2.4, so it's actually further out. 2.4, somewhere around there. I'm trying to make that 40% of the way from the second orbit to the first, second to the third. So it's going to go out as such. And then it's got to come back down, because that's what a sine does, right? The sine values in the second quadrant and the first quadrant are the same. If you don't believe me, calculate it at 3 pi over 4, and then calculate it at pi, and you'll see that it closes back up. But its behavior after this is quite different from the black curve's behavior. So for example, try to come up with the r value that makes this 0. Sorry, the theta value that makes r 0. And that theta value is when sine is equal to -1/2, which happens at 7 pi over 6. So that means by the time we hit an angle of 210 degrees, or 7 pi over 6, this red curve should already have closed back up to the origin. So it's very shallow. You can see that the red line is a little bit less low than the black line. Another way of saying it is the red line is closer to the origin. Now, if we calculate bigger values, such in the third quadrant, you'll see something strange happen. So let's do 5 pi over 4. At 5 pi over 4, this will be 2 times sine of 5 pi over 4. So that's 1 plus 2 times roughly -0.7. And that'll turn out to be -0.4. That's a bit strange, but to have a negative radius, here's the convention for negative radius in polar form. So we go to 225 degrees, or 5 pi over 4, we're pointing in that direction, but rather than march out 0.4 units, we actually go backwards by 0.4. So if we're pointed in this direction, we're going to go back by 0.4, which will leave us actually in the bisecting the first quadrant, but will be 4/10 of the way from the origin to the first orbital line there. So the curve goes up. And then at 3 pi over 2, this will be 1 plus 2 times sine of 3 pi over 2, which is -1. And now we're actually in the most negative territory that we're going to be in for this particular function, which is -1. So that means orient yourself down to 3 pi over 2, but go back exactly 1 unit, and you'll get there. So actually, almost all the points, as I'm using these terms loosely, but after 7 pi over 6, all the angle values after 7 pi over 6 actually produce values not in the third quadrant, but in the first quadrant. And then if you plug in the fourth quadrant, you'll see the same thing happen. And then this image will repeat that shallow arc afterwards. So this thing has a term as well. It's a French term called a limaçon, with an inner loop. So it's got this inner loop to it. I'm not too concerned with the terminologies though. So I guess the major thing to learn or to think about is with these trig functions is you have to kind of decide between the constant and the trig function who's winning or who's dominating behavior. In the case of 1 plus 1 sine theta, there is a point where they're co-equal, and that's at 3 pi over 2. So that's why the black curve closed in on itself, but did not cause a loop inside of the image. Once it hit 0, at that point, that was the smallest the r would ever get. Then it began to be positive again, so it sort of repelled away from the origin. Whereas in the red one's case, the strength of this coefficient, since sine can become -1, all the other values obviously between -1 and 1, but when sine's -1, 2 times -1 overpowers the 1 and causes a negative r value, so instead of heading down, we actually have a negative r value. We could graph all kinds of things on here. If the graphs are not sine but cosine, instead of heading up, they're going to head out toward the east here, towards 0 degrees. If we were to negate these sine functions, it'll be the same image, but it'll just flip over. So in summary, the rectangular form tells you how much to go over and up by, whereas the polar form says, okay, orient yourself and then walk out to that point. Now, part of the point of this is that not all functions are easily represented in rectangular form. One of them was x squared plus y squared, and that was also known as r equals 1. So let's go back to this equation in black, 1 plus sine theta. So if we take r equals 1 plus sine theta, if we wanted to try to convert this back into rectangular, the first caveat is it's going to get worse. But we're going to use these 3 items. So one inclination is to square both sides. Turns out that's not the best idea here. Better idea is to multiply both sides by r. So if we multiply by r everywhere, we'll get two good things happen. One is you get r squared, and r squared is exactly x squared plus y squared. Another really good thing that happens is that r sine theta happens to be y. So that's plus y. And I've left room here because we need to replace r. Well, if you go back to this equation, r is simply the square root of x squared and y squared. So we take the square root of x squared plus y squared. Now, I do agree that this black polar equation and the red polar equation are not exactly trivial. But if you take some time to think about their coefficients, where the graph will be oriented, either north, south, east, or west, will there be an inner loop or not, you can kind of get a feel for the shape. If, however, I said to you, okay, take not that thing, but this rectangular form, and I said, tell me what shape this thing makes, you're going to have a very difficult time analyzing it just in terms of x and y. And even isolating y could be tough, so there is really good use out there for polar. Now where this is all going to, so I told you where we started, which is to convert from rectangular to polar, giving you rationale as to why it's useful. Now in a calculus context, the next idea that we'll develop is how to take derivatives of these graphs. Important note is we're not going to do just simply the derivative of r is 0 plus cos theta. Because that is the rate of change of r with respect to theta. We still want to be able to go to a point and name its tangent line. And that thing has a slope. And that slope is still dy dx. Because if you notice these axes I put on, they're still the x and y axis. There's nothing changed about that. It's really just a different way of translating or naming this function to be a different way that's a bit more easy to work with. So we're still going to be interested in dy dx. So our next challenge is going to be taking these equations, especially these two, and producing a dy dx expression from them.